Good afternoon, everyone. Welcome to your day 5 of your international workshop on machine learning and deep learning hands-on. And I welcome resource person Subrat Swain Kumar sir for the day 5 session. And I request the resource person to start the session.
Hello. Good afternoon, everyone.
Good afternoon.
Today is the day 5 of our this 6-day long workshop, and today we'll be covering autoencoders and its application. So autoencoder is a kind of neural network that we'll learn today. So for that, let me set up my notebook and share my screen and take you to the notebook page. Can you see my screen?
Yes, sir.
Okay, great. So we'll start with the topic autoencoders. And before starting the topic autoencoders, let me show you guys one of the results that was running yesterday and it was completed. So did anyone like tried running the cells that I showed yesterday? Like if you had run, you could have got the results. We saw on day 3 that while using CNN while using ANN for classifying very complex images such as the Cipher-10 images, which is a collection of real-world images of 10 different classes. So we saw that the accuracy was not good, and we saw that while using CNN, we sort of minimize the image in such a way that it preserves all its property. And we saw that in ANN, the accuracy was coming out to be 51%, and in CNN, it came out to be something around 73%. And so then yesterday we discussed about all these state-of-the-art models where they are known for their good performance, and we saw that using yesterday I was trying to convince you about the fact that these models are well trained and they preserve all those properties and all those shapes and sizes of the uh, image in dataset. And and if we leverage those models to predict our Cipher-10 dataset by just changing the final layer, we'll be getting good results. So, but due to time constraint or like it was the resource constraint, we couldn't see the output of these models yesterday, but I ran them. And as you can see, the VGG16 model that we used yesterday is giving a accuracy of 87.22, which is a large jump over the past accuracy, which was 73.38, almost a 15% or 16% improvement on the prior accuracy. So if you run similarly, if you run these subsequent blocks, so this was the code for VGG16, and if you use Google Net for image classification, you can achieve similar results like VGG16. So ResNet, AlexNet, and GoogleNet will give you good results as well. So let's just come to today's topic, which is autoencoder. Before getting started with today's topic, I'll start by talking about the, uh, the 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 prior things that we have learned. So story so far. So we started with this the concept of x and y, and we saw that given a pair of x and y in real world, we generally face this problem. Given a new x, what will be the new y? So starting from this problem, starting with this problem, we sort of try to figure out how to find out what is the relationship between this x and y. So we sort of try to find out the relationship between x and y, and since x and y is related by this y equal to fx, we sort of try to find out what is this f of x. And we, so to know this relationship between x and y, which we call a data set, we first sort of tried with ANN. Then we tried the same ANN for images as well. So we tried ANN for tabular data. Then we then we used the same ANN for the image data as well. And then we saw that image data is very complex as compared to tabular data, and ANN is not a very good method to apply there. So then we learned about CNN, and yesterday finally we saw how this CNN has evolved over time to get better and better, and how this a small new concept that was developed and introduced in this CNN in subsequent years led to a very good improvement in the CNN's accuracy. And we also did all those code walkthroughs and code examples along with the theory, where we saw that how when we trained a simple model with CNN, it was giving good performance, and how these colored images of cat and dog uh, failed when we used just ANN, and how we converted how we created a custom CNN, and how we got better accuracy in comparison to the prior methods. And yesterday we saw how this state-of-the-art methods state-of-the-art models surpasses the custom CNNs and gave us the state-of-the-art results in the respective job. Today we'll be learning entirely different concept, where the goal is not to predict or classify. So if you could recall, so the task that we had in our hand was given x, what will be the y? So you find y given x. So this is the thing that we were trying to find. That is y given x. But if you see clearly, so we're just trying to predict y, and y can be anything. It can be numerical, or it can be numerical, or it can be like categorical. If it is categorical, it is a classification problem, and if it is numerical, it is a regression problem. But if you could recall, we also talk about something called unsupervised learning, where we have X only and we're trying to model X or learn only X. So when we're talking about learning only X, so what are the things that we can learn only from these features? So what can we learn from the features? So the question is, let's say we have only features without any labels, then what we can do? So if you could recall, I gave an example about this news headlines and how to sort of cluster them. So if you recall, so there was let's say there are thousands of news articles, and in those thousands of news articles, we there is new news article of different varieties, and but we don't know those varieties, but we just know that they are different varieties. So what happens is that when we sort of try to categorize them, we don't have any Y here. So we just have only news headlines, that is our X. And we need to categorize that into different groups, like these headlines belong to some group, and these headlines belong to some group, and this headline belong to some group. So this type of task is called unsupervised learning, where there is no supervision, where there is no Y. So one of the primary uh, method in this unsupervised learning is the anomaly detection. So why we are discussing anomaly detection? Because so we will be learning today a new architecture of the in the neural network family uh, uh, that is called autoencoder. And we will see how this autoencoder facilitated so many different things uh, uh, just by just with this simple architecture. So we'll start with autoencoders. And autoencoder, so if I define formally, autoencoder is a neural network that tries to reconstruct its own input. So this is the definition, but I will explain it now. So let's say this is my input layer. And the input layer size is, let's say, n. So we want a network in between that will give me the same n in the output. So here is a network that will take nx, so this is x as input, and in the output it will give me this x dash, and the dimension of x will be equal to the dimension of x dash. There is no y involved here. So it is a neural network that tries to reconstruct its own output. Like it will just reconstruct this x, and this is the autoencoder. So can any of you tell, like, so does any of you have any questions just by looking at this definition? Because this definition is very simple, and you might be thinking why, like, if you are just taking x and getting x in the output, so what is the point of that? We had already x. Then what's the point of creating x dash, which is exactly same as x again? So can anyone, like, write in the chat why this might be the case, why we need this? Or if you don't, like, get it, you can just write that why in the chat, so that I will see, like, if you could guess it correctly or not. Why this input and output are required when they are exactly the same thing? X and x dash, they are exactly the same thing with same dimension and everything. Why should we like, require such a neural network which just take and repeat the same stuff in the output? To avoid information loss. No, the information loss, uh, uh, no, the information loss that you are saying, so it's just taking this input and trying to recreate that in the output. So so just think it like this way. So let's say there is an image of a 7, and let's say you expanded it and made it like this, and there'll be 784 dimensional, and you pass this to the next layer, and when you pass to the next layer, it will be something different. So um, uh, it will not be 7 again, it is something different, and then you're again trying to get back this 7 here clearly. Okay. So I guess accuracy won't be the correct answer, because we're not dealing with y here, so it's just only x. So since it is only x, there will be no accuracy. But yeah, so efficiency is not the correct answer. So I'll now describe this autoencoder. Give me some time. Give me a minute. I, I'm sorry as well. I'm just having a meeting.
Yeah, I was gonna ask you, if you remember.
Yeah, no problem. Yeah. Hello. So I'll now describe this. I'll describe this autoencoder in detail. Okay, so I'll define this. I'll now describe this autoencoder. So what happens is that we take an image. So I'll just go with the 7, and we flatten it. So if it is a big image, we need not to flatten it, but I will flatten it now because it's a small image and it is coming out at 784. And I'll pass it to a layer. Let's say the size of this layer is 256. And then I pass this to the next layer. Then I pass it to the next layer. Let's say the size of the this layer is 100, and let's say I take this layer that is 100 and I pass it to another layer that is same as 256, and the output is again 784. And from the 784 dimensional vector, I can reconstruct my 7. So the point of creating this diagram is that, so we are sort of trying to uh, pass this entire thing in this unit, and sort of trying to reconstruct that. So there are certain components of autoencoder. So this is called an encoder. This is called an decoder, and this has too many names. So this is called hidden layer, or Z, or latent layer. Z is a variable that we denote, and the encoder is and this is called the input X. This is called the reconstructed output X hat, and yeah, this hidden layer is called Z. This hidden layer output is called Z. So they are the components of autoencoder. So what happens is that when we pass an input to an autoencoder, so it takes the input and it sort of encodes it. So just get this sentence. So the information of 7 is stored in 784 neurons. So in the next step, you are trying to tell the network that please store all these 784 information that is present in 784 neurons inside these 256 neurons only. And the next step, you are trying to tell that please store this 784 dimension worth of information in just 100 neurons. So you're trying to tell someone that take this 784 neuron worth information and store it in 100 neuron worth cell, which is like 7 times less. So as humans, just think about it. If you are uh, given a, a full plate of food, and in that full plate of food, you are and let's say the amount of food you have in your plate is 10 times more what you can eat. So what would you do? Like, what will you do as a human? So let's just think it of in that way. So let's say your favorite is chicken and mutton, and the plate is filled with chicken, mutton, but along with that there is paneer as well, and there is other type of snacks as well. There is rice as well. There is parota as well, and so all these things are there in this plate. But and also there is biryani as well. And let's say you like the biryani most, and you don't like, let's say, uh, uh, let's say paratha, or let's say you don't like roti. So what will you do? So this plate has 10x more food than what you can eat. So what will you do? So you will eat those foods which you like. You will eat those foods which are important to you. You will eat those foods which you love. You'll not go around and eat rotis just because you have to fill your. It's not like that. You will start from one side of the plate and you will go till the point where you will fill, where you are full. No, you will eat your favorite food first, the food which are important to you, and then you will leave all those foods which you don't really eat, or which you can eat in very less money. So similarly, when this network is fed with this 784 dimensional information, and it was asked to compress it to this very small 100 dimension. So what it does is that it sort of it sort of tried to pick all those important information that is there in the image, and try to uh, forget the information which are not required for it. And so in one moment I will let you know what are the important information, what are the not what are the information that are not important. So when I so when this is getting passed to the next layer, the next layer, this says that, okay, so I have this 100 neuron worth of information, but I want you to, like, create 256 dimensional worth of information in it. So what it will do, it will take, since it has all the important information in this 100 dimension, it can recreate this 256 dimensional worth of information, because it has all the important ones, and it can just fill the gaps for all the unimportant ones. And similarly, by doing a similar operation, you'll get 7 years. So the point of like telling all these things is, I think, is that this network tried to filter out the important information from the image, and once it got an important information, all the important information on the image, it will try to recreate all the unnecessary stuffs by just because it has all the important information. So did you get the idea what I'm trying to say here? If you get it, you can comment in the chat. If you also don't get the idea, you can comment in the chat. A great question. Satwik asked, but what if the important information is more than 100? What 100 can accommodate? So, so let's say in this image, so we'll just, this is not a right way of, like, quantifying the information, but for the intuition check, let's say this 7 has 784 dimension worth of information, and if you put it in increasing order, it will take top 10, it will take top 10 worth of information, so top 100 worth of information, and keep it here in all this cell. What if the cell size is 90? It is same as saying the information is more than 100. So what it will do, it will arrange all the information in increasing order, and it will take top 90 of it. So it actually do not arrange this, it actually learn this important information inside this network. So initially when you do not have a trained version of autoencoder, it will store some random information. So once you have some random information, it will not be able to reconstruct 7. So when you train initially, and in the first iteration itself, it will not be able to reconstruct 7. But if you sort of uh, train it for 10 epochs and then test it, then it will be able to figure out what are the important information in this image, and from that only it will be able to uh, figure out what will the reconstruction is. Okay, I think you understood it. Can it okay, so sir, can it lose somewhat important information? Yes, if you force the network to learn everything in one unit, so instead of 100, let's say you put 1 unit here. So you're just asking that learn everything that is there in this big image in just one number. So it is not possible. So it will of course lose information, and it will not be able to reconstruct the 7 very carefully. The more you increase the size of this hidden layer, the more it can accommodate. But we don't want it to be like very high dimensional. We want it to be less. So this is the way autoencoder works. But I will let you know what is the advantage of it. Why do we need this hidden layer of a minimum size among all these layers, and what is the purpose of this hidden layer, and what we will do with this 100 dimension. Okay, great. So let's just go to this next thing, which says that what are the important information and what are the unimportant information in this image. So if you have went to the home and Googled, you must have saw that this MNIST dataset. It is a dataset of handwritten digits. So it starts from 0, 1, 2, 7, 8, 9. So if you see all these images, what's common in them? The common thing that you see in all these images is that there is a number in the center. See, there's a number in the center in all these images. So there are a total of 60,000 images in MNIST. And if you just see if you see all these images, they have one thing in common. Everything is in the center. Every number is in the center. Every number is in the center. Apart from this number, everywhere else is blank. It is blank. So if you could guess, so do do put in the chat What do you think is an important information in this image? Is it the number for the position where the number is lying, or is it the background is blank? Great, the number. So it's very easy to see that in this. So very easy to see that we need to remember that the structure of the number is in the center, and it is a complex data to understand. But apart from that, it's all blank. So do you think, is it like, if let's say 80% of, or let's say 80% of the neuron, 80% of the uh, pixel is blank, and 20% is number. So can you say that if I just assign one or two neuron to remember this fact that 20% is number and 80% is just blank, so I can just assign. So if you see here, out of 784, around like 600, around 600 pixels are blank. It has same value. Like if it is a black and white image, it is all black and numbers are white, so it is all zero. 600 pixels are zero. So do you think it's a effective way to like uh, learn the information, or we can learn that okay, 600 are black and these are the white in these places? So if you see these 600 pixel which are blank, we don't need actually 600 units for that. We don't need 600 units to remember that all these pixels are black. But so why we don't need? Because this blank is same in all the images. If you see, these all are same. So I can just, so since this autoencode will be trained for all the images, they all have in common is that there around them there is blank space. So to remember that, it can use only one or two neuron and can remember that. I mean, I'm not saying that it will use one or two only, it can use more, but just to understand, you just see that it can uh, like remember this as okay, in all the images there is around black space around this. So it's a way of remembering things. You can say that when you are sort of trying to remember 3-4 people, you can say that okay, all those people uh, goes to the same college, and there will be some difference. He is taking this course and he is taking that course and he is taking that course and he is taking that course. So it's like that. So when you have information across the dataset, common to all datasets, you can just remember them as a whole. So you don't need to remember all those things uh, uh, separately. But since you're training this model with all these different images, it is crucial to remember that different different numbers have different structures. So this has different structure, this has different structure, this has different structure, and this has different structure. So every number has different structure. To remember that, we need more neurons. So, so this 100 neuron that we provided in the hidden layer, it will be responsible. So it will be mostly responsible for understanding and sort of capturing the structure that is there in this number between 0 to 9, which is lying in the center of the image, rather than spending its time or spending its resources remembering that there is a blank space around the images. So I think I'm clear. Like I think I made it clear. But you still have if you have doubt or you didn't get the idea what I'm trying to convey, please put it in the chat. Like how this thing is like intuitive for you. So if you could understand, you can also write. I understood. And understood. So what we do if the pixel is blank, but what if none of the pixels are blank? Okay, understood. What to do if the pixel is blank? Okay, so you're telling that if the pixel is not blank, and you're saying that if there is something else around this object, and it varies from object to object, so there will be something else here, and there will be something else here, and there will be something else here. You're telling like that, right? Yes. So when you see, like, different images which are very much different than one another. So this is an example where you see uh, almost all the images are 60 to 80% similar. Only the numbers are different. Even if in the numbers 7 and 9 are not very different. You just take 7 and like add a line, it will be 9. So it's not very different. The difference is just this part. But what will happen if the numbers are the images are not very different, so are very different, and there will be something around this 0, there will be something around this 1, and it will be different for one hour. In that case, training an autoencoder will be a tedious task, because it doesn't have any information which you can lose. Everything is important, everyone is different. So in that case, this hidden layer size will be bigger. So just to be like, just to make the numbers clear, for this data set with 784 dimensional input, we can use as low as 16. So you can put 16 dimension here, and it will work fine to recreate 7. Or even if we can go till 10, we still can see good 7. But for this, when you said we might need 200 or 300 units in the hidden layer to make it correctly. Yeah. So this is the case, and this is the way, like, people have designed autoencoder. But so still this is the cause that I this is the um, uh, this is the idea that I said, is how this autoencoder is taking 7 and how it is compressing, and by compressing, what it means to lose the unimportant information and to preserve the important ones, and give out this 7 where this 7 is same as the original 7. So you might be asking, what is the use of it? What is the use of this autoencoder, where we can, if we can have this 7 earlier? So I'll just go to the first use case. That is, so one use case that we saw is reconstruction. One use case that we saw is reconstruction. We can get back the original input image. So reconstruction. But so why should we reconstruct? Second thing that we learn now is compression. Okay. So let's imagine. So you have this image of numbers in your mobile, and let's say one image is one image is uh, one image has a size of let's say 1 MB. Okay, so if you have 60,000 images, if you have 1,000 images, so your size will be 1,000 MB, which is around 1 GB. But so let's say so one way to store is that just store all the images, which will be 1 GB. Let's say you have this autoencoder where you have an encoder E, its size is let's say 10 MB. You have a decoder D, its size is also 10 MB. So what you can do is that you can sort of take all your 1,000 images and pass it to encoder. And you get all the Z's. So when you get all the Z's, and let's say this Z is like 10 times smaller than the input size, and let's say you need 0.1 MB for that. So when you need 0.1 MB for that, you the total size of your file will be 0.1 into 1,000, which is 100 MB. So what you do is that instead of storing 1,000 images, you store the encoder, you store the decoder, and you store this 1,000 Z's, 1,000 latent layer representation. And when you are asked for that image, what you can do, you can just pass this Z to the decoder, and get back your 1,000 images. So in this way, the total memory that was spent here is 1,000 MB, or which is nearly 1 GB. But here, in contrast, you will spend only 100 plus 10 plus 10, 120 MB. So did you guys get the idea, like how this autoencoder will help us in reconstruction? If you get the idea, just put in the chat that you got it. Yeah. So another way of using this compression idea is that, let's say you have you want to send data over a network, and let's say you have images here. What you can do is that you can place an encoder here in this end, which will take this image and encode it. Then you can pass this encoded image through the network, and here you'll have a decoder which will take this image and will reconstruct it. So in this way, you can send these things very fast over the network, where sending a large image would have been would not have been like very fast. If Z stores only 1 MB, how it reconstruct all the 1,000 images? No, like each Z is 0.1 MB. So here the image is 1 MB. When we passed the image to encoder, let's say it compressed the image by 10 by factor of 10, and so if you compress the factor of 10, 1 MB will be like 1 by 10 equal to 0.1 MB. 0.1 MB is the size of one image, and you have 100 images. So this 1,000 images. So this 100 equals to 0.1 into 1,000. there is any limit of MB for Z? No. So what I mean to say is that if you increase the size of autoencoder, it's not like that. So I have already mentioned you that this network is depends on the structure of this network depends on you. If you want to keep this dimension as 100, it's fine. It will be 100. And let's say 100 to keep 100 neuron, you want 0.1 MB. So let's say in some computer it might need more or might need less, but the idea is that it will still be lesser than this input size. So let's say someone design a autoencoder which is whose input this hidden Z is 200. If it is 200, then it will again be more like it will be 0.2, let's say 0.2, and the total size will be 0.2 into 1000, which will be 200 MB. So it is less than 1 GB, still less than 1 GB. So what I'm trying to say is that depending upon the architecture that you choose, depending upon the this size of these layers that you choose for your task, uh, the size of encoded G and the size of all these things will depend on that. There is no limit on the MB of Z. It's just that whatever you choose accordingly, you will see the size. How it decides which information is important and that need to be preserved. So good question, like how it decides. So for deciding this autoencoder, so you have to train that. It's not like that you will pass it and it will uh, give you the reconstructed output. So if you put, so what is in between this? So these are weights. These are randomly initialized weights. When you train it, you will try to find those pair of weights which will minimize the distance between this image and this image. So you are sort of trying to find. So remember, I showed you a graph here in day 1 itself, day 2, I guess. Remember, I showed you this graph where I said I want the error to minimize and I want this error to be minimum. And for that, so this is the error curve or the loss curve. I want it to be minimized. So wherever I am, I'll just go down till I go to the lowest point of error. Similarly, in autoencoders, when we first declare this, when we first declare this yeah, when you flash declare this model, it will have random weights. It will have random weights, and the weights will be somewhere here in the error curve. So what we need we need to find those weights which will minimize the error, which are here. So we have to travel this much distance to find the minimum weights, find the weights which will minimize the error. So to do that, we need to find what should we be minimizing. It's not like that if we minimize anything, it will work. So we should look for the things which if we could minimize, it will. So with that goal, it can improve. It can improve the weights and it can update the weights to get the optimal weight. So one of this way is that minimizing the distance between this 7 and this 7. So if you write the loss as x hat minus x, the L2 norm of x and x hat minus x, then it will try to, so this is the loss. And when you design the loss, when you put the loss, so you say that minimize this. So this will be minimized. This x hat minus x will be minimized, and it will get minimized to this to minimize to find the weights which will optimal enough to learn the important features. Another way of answering a question, how it decides which information to which information that needs to be preserved. So let's say it doesn't know. let's say it start with random information, and let's say it kept all this blank area information in the first iteration. So when we will be training, we'll be training it for a lot of number of iteration. Let's say in the first iteration, it sort of took this these are information. So when it will took these area as the important information, it will not be able to reconstruct 7. It will be able to reconstruct only noisy 7. It will not be able to reconstruct the actual 7. If it is this is not an actual 7, this will be higher, because there is 7 in one end and there is not a 7, like very hedgy 7 in another end. So if you take a difference, pixelized difference between these two images, it will be higher. And our goal is to minimize this loss, like keep this low. So to keep this low, the A new and B new, the weights, when it will updated, it will be able to find those weights which are optimal and which are sort of give you the minimum error. So using that, using that, it will update the weight, and using that, in the final iteration, it will be able to figure out the optimal weight that is required to know which information to preserve and which information to lose. Did you get it, like what I was trying to convey to your question? Okay, great. So we now saw the reconstruction and compression, and so before moving forward, so I'll just try to show you the types of autoencoder. Okay, so the one we saw now, where this was the case, is x test, x hat, and this is z. If dimension of x is greater than dimension of z, it is called under complete autoencoder. One second. And let's say you have an autoencoder input is x, output is x test, and z. And if dimension of x is less than dimension of z, we call it over complete autoencoder. We call it over complete autoencoder. So you might be asking, what's the point of this? We are sort of taking small information and we're sort of trying to make it more uh, uh, you know, more computationally heavy. So we're sort of uh, more storage heavy. We're sort of taking small amount of information and we're telling that you have this small amount of information and just store it in large area, which is easy to store. So that's the point of that. The point is, so it has a different application rather than compression. It has something called super resolution. So it is one of the application of this over complete autoencoder where you have where you want to achieve super resolution. So what is super resolution? So I'll just tell you let you know briefly. So when you sort of see a image, so you must have seen this in uh, LinkedIn or somewhere where people have posted some images, but those works were the recent advanced version of the super resolution. But the idea started when the idea started, they sort of started with this, and it was one of the way they achieved this. So let's say you have an old photograph. So if you could remember, old photographs were not that good. So they were very low in resolution, and they sort of were missing very tiny details in your photo. So if you see a picture of your mom or grandma, you can say you can see that the details in that picture is very less, and the details or the clarity in that pictures is very less. So the goal of super resolution is to take an old image and create another a very clear image out of it. So take an old blurry image, or take an bold not so colorful, or not colorful, take a bold and like very bold image and sort of try to find a better image version of that. So to do that, what we do is that we take this input X here and we try to sort of create a bigger image out of it, and the bigger image will be such that from which we can get back the smaller image. So it's sort of adding noise in the image or adding things around the image, and it is not adding those noises. If I add that, it is breaking the continuity of the image, or it is breaking the semantic semantic property of the image. Without breaking the semantic property of image, if it is adding some noise, that is allowed. So so to do that, we use this leverage this over complete autoencoder, and once it is trained, we can just pass this our old image to the encoder, and in an output we'll get a brand new image. This is one of the way of using over complete autoencoder, but there are other applications as well. So now we'll talk about the activation functions and loss functions that are used in autoencoder. So I'll be quick because we started late today and because of an emergency. So yeah, so I'll be talking about loss, or I can say the activation function. First, I'll talk about activation function. The quality of image X and X dash be same. Yes, the quality of X and X dash will be same. It's just taking the image and trying to do the same thing in the output, keeping in mind that it has to learn a representation in the in the middle, which will be useful for our task, for our for our help. And this is also called representation learning, where we are learning a representation of the input data or an input image, but that representation is like specifically designed to cater our needs. Okay, good. And so let's just start talking about this activation function. So in a typical neural network, we can apply activation functions such as ReLU, sigmoid, and tan H. So just remember that in the hidden layer Z, we use sigmoid. And if the input is binary, which is 0 or 1, we use sigmoid at the output layer. Why? Why do we use sigmoid at the output layer? Because sigmoid is an activation function that squares the value between 0 to 1. So that we can, if it is in this this is the output layer. Is the output layer. If we use 0 and sigmoid function, all this value will be between 0 and 1. Since it is binary, 0 or 1, and our this value is between 0 to 1, we can round this off to make it the values between values of 0 or 1. This will be curly braces. Okay, great. And if input is real, that is real number. If it is real number, we will use tan H as an activation function at the output layer. So this is all about activation function that we can use in these layers of autoencoder. Yeah, it's not that important, but I just wanted to let it know because I already said in the earlier lecture that we can use any activation function that we want in the network, but certain network has certain rules, we cannot use different activation function in some areas, otherwise it will not give good performance or good accuracy as an output. Then coming to loss function. So just before some time I mentioned that I want my X and X hat to be similar, right? So you want two images to be same. So how do you measure the distance between two images? How do you sort of say that these two images are same? One way is that you take each pixel of one image and each pixel of the second image, and you sort of try to find the Euclidean distance between those two, or you can say second norm. So X hat minus X L2 norm. That is one way of dealing with it, and we want to make it similar, or we want to make this distance between them smaller. So that's why it is our loss function. So whatever is the loss, we want to make it smaller. So whatever you want to make it smaller, put it as loss, and this is called MSE, mean square error. And this is useful when the image is continuous. So this is useful if X is a real number. Okay. If X is binary, I mean, if the image is only 0 and 1, so the loss function that we use is called cross entropy loss. It is cross entropy loss, and for binary we use BCE, is binary cross entropy loss. So while designing this, so while like sort of using this, and if you see the image is binary, we'll use this loss function, the binary cross entropy loss function. And apart from that, if x is if x is binary, we use cross entropy loss, and the formula for cross entropy loss is that minus E equals to summation of all pixels yi log yi 1 to n minus x. This is called negative log likelihood also. NLL is the same thing with BC and yeah. One more thing, this activation function, if it is real, so tan h is one option. We can also go for, because tan h is one option when the data is normalized. If normalized, if it is not, we can use identity as our activation function, because which means no activation function. If not normalized, then identity. Or no activation function. Okay. And is the loss function that we'll use, that we use when we're sort of designing this. So this ends the discussion of autoencoder, and we will sort of see there is another application that is called denoising autoencoder. So, and there are other types of autoencoder as well. There is sparse autoencoder, contrastive autoencoder, and variation autoencoder, and all this stuff. But we'll not go to that much level or that much depth. So I will only discuss denoising autoencoder. But since denoising autoencoder, if I discuss it, it will be too much. Like it will be like defining 2-3 more concepts. So what I will do is that so after this point we will do some coding of normal autoencoder and see how it is working. And after that I will let you know the theory of denoising autoencoder, and then we can start coding the denoising autoencoder as well. So before pausing the session, if you have any doubts or any concerns regarding the what we discussed now in this first 1.5 hours or something, so you can put in the chat now. We'll discuss the doubts now. So some lights on the application. So one application was compression, one application was reconstruction, and there are numerous applications of autoencoder, which we sort of do it every day. But yeah, so another is denoising, which I will discuss later after this point, and another is anomaly detection, where we are sort of detecting the anomalies by just using autoencoder. Yeah, so anomaly detection is there, reconstruction is there, then there is denoising, then there is compression, and so there are the 4 major application of autoencoder. Apart from that, we use autoencoder as a like supporting step in ML workflow, where we'll use autoencoder and then the output of the autoencoder will be used by some other model. So if it is not directly, it will be used indirectly. And by inspiring, getting inspiring from this autoencoder model, people started looking towards encoder decoder model. So encoder decoder model, where there is an encoder and not necessarily it is smaller or something, it will encode something, and this decoder will take this and decode something. So the beauty of autoencoder is that the encoder is just a mirror image of decoder. To put a mirror, the architecture of encoder will be same as decoder. But when people started designing different encoder and different decoder, so encoder can be anything and decoder can be anything. So then they started seeing better results as well. And also, this is not the application that I'm telling, but encoding and decoding is a fundamental concepts where we encode concept and decode it to something else. So here it was just decoding it to same image. But what you can do is that, so one application and that I will let you know is the transformers. If you heard transformers, so transformer where these models where the information is first encoded by three or so 8 encoders, and all this information is then combined to get a final encoded value. And from this encoded value, everything is decoded and combined to get a output. And this led to this development of transformer, and the paper discussed this idea is called attention is all you need. Attention is all you need. And this paper started with this idea of encoder and decoder, and this idea of encoder and decoder evolved forward to give rise to bigger transformers, and these transformers sort of something that powers ChatGPT today. So if you look into the architecture of ChatGPT or any GPT model, GPT based models, so it is all started with transformers. So they started with this autoencoder, and then they evolved this to encoder decoder model. So if you look into the ChatGPT, the full form of GPT, so actually this GPT is stands for generative pre-trained transformers. So it's a transformer that is used in this generative context. So what happens is that so suppose you have an image and you want to caption this. So you want to say something about the image. So when you train this sort of model, your X will be the image and Y will be the caption associated with it. Your X will be the image and Y will be the caption associated with it. So when you train a model like this, you encode. So you want to tell the machine that this and this are same. The image that you see here, the description that you see in the other side are the same. To do that, these two, like image and text, has to speak the same language, because image is something different, text is something different. They're not speaking the same language. To understand that, we need a common language. So this common language is provided by this encoder, where the image will be passed to the encoder and we will get a encoding, and from this encoding we'll try to generate the text out of it. So this encoding sort of act as a bridge between these two type of data set here, and they communicate with each other, and they sort of try to figure out the encoding from which a text can be generated. And using this, we can sort of create this encoding decoding model where we can pass our image and get the caption out of it. Similarly, the similar concept developed where this input can be any text and output can also be So input can be any text, and input can be any text, and output can be text as well, which is the model of transformer where you put some text as an input to the encoder. It takes and it encodes, and from it decodes and give you text as an output. So it's a generative model where you just give some prompt and get output as a text. Any other question? Great. So we'll discuss the two application of it. Like one is denoising autoencoder, and if we get time, we'll also see some animal detection with autoencoder. And till that point, like so, we'll take a 10 minutes break now, 10-15 minutes break now. So after I come back, we'll discuss those two things, and then we'll close the session for today. Thank you. So we'll now start coding the same. So I'll share this notebook as always, and you guys let me in the chat if you could access it or if you are facing any issues while accessing this notebook. So I put the link for this notebook in the chat. Kindly let me know if you can see the notebook and sort of access it. Please let me know in the chat if you can access it. We can proceed. Hello. Okay. So we'll start with our discussion of all coding autoencoders in PyTorch. So let me just remind you that you have to go to this runtime, and if you change runtime type in the hardware accelerator, you have to select T4 and then you have to hit save. And yeah, so after doing that, you have to import all this library and also check if the device is set as CUDA or not. So we'll do that first and see if it is compiling correctly or not. Yeah, so I'll just print the device. So when you print the device, you can see it is CUDA. So So we'll load and prepare the pre-process the data set, which is same as we did yesterday. To download the data and keep it inside the folder. And then we'll define the network. Okay. So while defining the encoder, so this is the class for defining the autoencoder model, and in the autoencoder model, we will sort of try to see like how this autoencoder model is working and all. And so for to do that, we sort of started with defining the encoder and decoder separately. So when you see this encoder and decoder, they are sort of up here like this. There is linear layer, and so I'll just show you how what this means in the paper. So when you are defining this autoencoder, so in a defining encoder, you're putting linear layer as so you're putting the first as linear layer. This line means you are defining a layer whose input dimension is 28 cross 28 and output dimension is 128. So like to follow that, what you're doing is that you're taking an image of 7. You are sort of expanding it to 784 dimension, and we are passing that to a 64, I guess. 64, 128. Yeah. And if you see next, then we put relu here, and relu is just activation function, so we'll just keep that. And relu here, and so after relu we have a linear layer of 128 to 64. So the code for corresponding that following that will be like 128 to 128 to 64. So yeah, so 128 to 64, and the next layer is again relu, and the layer after that is linear, which is 64 to 32. So this takes 64 as input and sort of compress it down to 32. So this is our encoder. These are entire encoder E. And now let's see what is the so we are using relu here, but we can change it to sigmoid as well. So you can change to sigmoid as well. And let's say so this is the input. So when we are having the output, let's see what are the things that we're using. So in the output, we are so not in the output, in the decoder, let's see what are the things that we're using. Okay, in the decoder part, the decoder starts with a linear layer of 32 to 64. That means in the decoder part, it will start from 32 to 64. It's just opposite of what you see in the encoder, just a mirror image. It is 64. If you see, the next layer is ReLU, which is the activation function. So we have to provide it in between. And the next layer that we see is 64 to 128, just a mirror image. And 128. And after that, you have 128 to 784. Look clearly, it's 128 to 28 plus 28, which is 784. And you get the 7 out of it, like that. So this is the way, like, we put our architecture. And how do we propagate that? The way to propagate that is that take x and pass it to encoder and get the z. So I can name it to z. So it's a variable. We can name it anything, but for readability, I'll just name it as z. So we got z here, and we pass the z to the decoder, and we get the x hat. So I'll just rename it as x hat, and we're returning x hat from this method. So forward function defines how a input will be passed to the neural network, and how we will get back this as an output. So as I mentioned earlier, it was like take the input and pass it to the encoder, get the z, use 32-dimensional, and pass that z to the decoder and get back the original image. So this input, so we took x, we passed to encoder, we got back z, and we took z and we passed to decoder to get back the x hat. So this is the idea, and this is the like idea behind the autoencoder. We pass, we encode, we pass to encoder and we encode. Then we take that encoded input and we got back the x hat. Then coming to training. So training is pretty simple, because we need to we have declared the model. We need to make an object of it, and then we have to define the loss and the optimizer. The optimizer, if you have marked, it's same in all our case. It's Adam. Adam is the state of the optimizer to update our A's and B's and the new W's. So we're using that, and in the form of loss, we're using MSE loss. So as these images are real number, we're using tan H at the output. So remember, I said that you can use identity or tan H in the output layer here if the image is real. So it's tan H or identity. So I'm using tan H as of now, and let's see. Yeah, let's just run this training code. Autoencoder is not defined. Okay, we'll have to run this code first. Yeah, and this cell, we ran it. This time. Then coming to the next part. Come to the next part. So actually, someone was asking about the recorded videos. I have said I earlier I said a folder where you can see all those videos, but recently I have shared with ma'am in the group a folder where you can find the videos and everything, I guess. So I'll just show you guys what that is. So this folder I have shared with the link to this folder I've shared with everyone. So here you can get the presentations, and then there is recorded videos of day 1, 2, 3, 4, and today's videos will be uploaded there as well. And then there is link to Jupyter notebook, where you will find the link to all those notebooks that I sort of ask you to use every day. Just make it bigger, better. Yeah, and this is the link for notebook. Okay, and so there is link to notes of all the days that I have taught. You can see them in different sections here, and then there is workshop schedule and workshop brochure. So you can find this. I shared this link to the folder. You can find this. Okay, coming back to our code, we defined the loss function and our optimizer. Now we need to train the model. So to train the model, we're training it for 10 epochs, and if you see the training code, it's exactly the same. We're getting the image, we're transferring the image to device because it is crucial to transfer the image, label, and the model to the device so that it can all the things will be can be done in the GPUs. Since there is no labels here, we're just sending the image to the GPU. Then we are making the optimizer as 0, and then we are calculating the loss. It is forward passing the image, we're calculating the loss, we're back propagating it, and we're updating the loss, updating the parameters. So I'll hit the training code now. It will hopefully train now. This might take a while. So meanwhile, I'll try to, yeah, so it will take a while, I guess, to train. And so after training, I have written code to, I think it will not take much time. I've written code to plot the training error. And I also written code to display the images, the original and the reconstructed one. So hopefully this will display the images. Yesterday I got a comment that to display the images at least, which is otherwise it is not so intuitive. So this code is running faster than yesterday because I have used GPU. So 3 out of 10 epochs is done, and you can see the loss is decreasing. Also, I have written a code to plot this loss so that you can see how the loss, is decreasing with time, and how we should always look for decreasing the loss. Okay, so just be with me for 1-2 minutes. It will be done. The training is done. Now I'll plot the training error. So as I said, so our goal is to reduce the error or reduce the loss in the model, and whatever our goal is and whatever we want to reduce, we'll just put it as loss, and this model, while training itself, it will reduce that. Let's just plot this loss. What I did is that I made a array of train loss, and I sort of added the train loss after every epoch. Now I'll just plot a bar plot to do that. So this is a plotting library where I just hit plot, it will plot my things. So you can see the training error, the mean square error is reducing with increasing the epochs. So the epochs are at the end epochs, the reduction started very fast and it dropped sort of to a smaller value at the end of 10 epochs. So it's crucial when you train something, you should always see for you'll always stop when the reduction in the squared error is not happening that very fast. Like it is not dropping fast. It is sort of stagnant and it is sort of plain. It's not reducing much. So then you can stop training. So for me, I just trained it for 10 epochs because we're running out of time. You can train it for 15, 20 to get better reconstruction. Then we have this little block of code to sort of show the input image and the reconstructed image. And if you could recall, we used only 32 dimension in the hidden layer. And if you see here, our goal was to get this exact representation of 7 or any other number given there is 32 dimension. So the question was, now the question is our model able to store what is there in this number 7 in just which were requiring is 784 dimension in just 32 dimension? Was it possible? So let's just see by running it. Yeah, you can see the left side is the original image and the right side is the reconstructed image. You can see it could easily reconstruct all this black that is there, but while reconstructing 4, it is a bit blurrier than the original 4, but still you can say that it is a 4. So I hope everyone got this. If you are running the code in parallel with me, you could have seen this results by now. If not, just run it and you will find this output. And do let me know in the comment, like if you have any doubt regarding this demonstration that I did just now, because the other demonstration that I'll be doing today will be just changing the data set or changing the architecture, nothing much, like on the idea itself. So in the chat, if you are not able to get this reconstructed image and original image, please let me know. Otherwise also, if you couldn't get any of the part, also put in the chat. Okay. So we'll sort of now move to a different data set where the data set is fashion MNIST. So fashion MNIST is a collection of data. So I just saw another image of 7. You can see that while reconstructing, it sort of created a little tail of 7, which is not there in the original image, because it sort of remembered that, okay, if it is a 7, there will be a tail in between. So that's why it's tried to put that tail. If you go to another image, it is 4, but it is trying to make that 4, but it's kind of look like 9, because it has remembered the information from all the digits, not just 4. 0 is well constructed. 9 is also well constructed. So you can just run this block again and again to get different random image, random digit, and its reconstructed output. Now we'll look at this fashion MNIST, where the goal is that we will be now the goal is that we'll be dealing with a different data set. It's a bit complex than this, where there will not be an image of a digit. There will be an image of this a dress, a fashion item. It can be a t-shirt, or it can be a shoe, or it can be a shirt, skirt, or like any fashion item. So to get started with this, let's just load all the libraries that is needed for this task in one cell. And load the data to our code. To download the data from the net. Then just define the autoencoder model that is there. And if you could notice, the autoencoder model is exactly the same that we discussed for the MNIST. It has this input layer, there is encoder layer and decode layer, and the structure of encoder is exactly the same: 784, 128, 64, 32. And also decoder is the mirror image: 32, 64, 128, and 228, 784. So you run that, then we'll define the loss functions and optimizers now. We did that. Then we'll do our training. That we have started the training, and we'll soon be seeing the results. Yeah, the training is done. Now we will see how the reconstruction is. Great. So we'll plot the training error now. As you can see, it is well trained and the error has reduced. And we'll plot the image now. As you can see, the image is clear, but let's just, yeah, it's not that clear as you used to see in ANN, like the MNIST. So MNIST one was better clear than this. So to make it a bit more clear, what I did is that I tried to train a CNN CNN autoencoder. So when you talk about CNN autoencoder, the uh, the idea is that instead of adding ANN, the artificial neural network layers, we'll add a CNN layers, and that will hopefully give us better results. So we train that using CNN. This is the code for CNN. We just defined a CNN layers here in the autoencoder. Everything else is same. Let's just wait for some time for this to get trained. We can show you the results. Let's just wait for this to get trained, and I can show you the results. we saw all these original and reconstructed image given by this autoencoder. Now we sort of see that ANN and CNNs are not that different when it comes to this very simple data. But if we sort of go for very complex data, then CNN autoencoder will significantly improve over the ANN autoencoder. I think I got a concern that I'm unable to access the recorded lecture. So let me allow me to share the link for all the entire folder where you can see sort of everything. In this link, you can get access to the folder. So where you'll get everything starting from presentations to lectures to notebooks and everything and notes. So just put in the chat like if you can access now the folder or not. Okay, great. So now we'll move our discussion from this practical session to one more theory that is left for today for completing this session. That is denoising autoencoder, and another application of autoencoder that is called animal detection. So those two applications, I'll start talking about them. First, I'll talk about animal detection. So what is an anomaly? So when you go into the definition of anomaly, you can say that anomaly is something which is different from everyone. So let's just think about the image of animals, like there is cat, there is dog, there is cow, and there is, so let's say you have an album and you have uh, pictures of all these animals, cat, dog, cow, and tiger and everything. So in that album you see there is a picture of bird. So when you see a bird in this album, so it makes you think, right? It makes you think that, okay, why there is a bird? So you are not, you are not like, normal. So you have been seeing only animals, then you start to see one bird, then you'll be like, okay, why this bird is here? So so this point of confusion, so this point of non belongingness is called anomaly, where in a data set, if most of the data is of one type and the rest like 5-10% of the data is another type, this 5%, 10% of the data is called anomaly. So um, so it is crucial to detect all these out of the box data, or out of this all this outlier, because this outlier can be like harmful for us. So in the task of anomaly detection, we sort of detect the anomaly, and we sort of figure out which of these images are different from each other, and which of these things are not fitting, not cannot be cannot be counted under this one hood. That is example number one. Another very popular example is your network anomaly. So when you sort of see an attack, so you must have seen, like, so how do people hack? So if there is a router, there is something called IDS, that is intrusion detection system. So when you see this intrusion detection system, what it does is that there is network coming from everywhere to this router. So suppose you are inside this network, home network, you are using your phone, you are using your laptop, and you are using your TV, smart bulb, and there is Alexa. So all these things are connected to this are a part of this network, and they are sort of communicating with the real world. So this is internet. So this is internet, and they're sort of communicating with this internet. This phone and everything is communicating with the internet. They are communicating with the internet, and they are requesting for some web pages or some songs when you want to play on Alexa, or the weather, and these are all the traffic that is coming from outside. Let's say along with this benign traffic, or the traffic that you have asked for, there are some malicious traffic as well that is coming from outside. The task of IDS is that it analyze all this traffic and drop all the malicious traffic from this point, and only let this benign traffic go to their respective devices. So in this case, this malicious traffic are the anomalies, and IDS here it sort of works as a anomaly detector. We sort of detect this malicious traffic and sort of flag it, okay, and say that it is malicious. So to do that, so you must be now getting what is the idea of maliciousness, and what is the idea of anomaly, and why it is crucial to detect these anomalies while working with real world systems. So to do that, let's just understand how autoencoder can be a part of this. So when we are talking about autoencoders, when I'm talking about autoencoders, it takes an image as input, it encodes it, then it try to decode it to get the original image. And there is no point in just getting this image. What it really care about is this intermediate Z, because we can get the compressed version of this input. So one property of this autoencoder is that if you have trained the autoencoder with number image 1, 1, 2, 3, 9, and 0, so it will only have learned to reconstruct these images 0 to 9. And if you trained an autoencoder with 0 to 9, and you are giving it a picture of cat to reconstruct it, it won't be able to do. Why not? It has taken all the important information from 0 to 1, and it has sort of tried to combine and merge all the unimportant information in 0 to 9, and sort of found a way to encode that. So when you show it a picture of cat, which is not a digit, not even a number, so it gets confused because it has never seen a picture of cat while getting trained. So when you ask that person, or ask the network to sort of reconstruct cat for you, so it won't be able to do that, because it has never seen cat in its entire life, and it doesn't know how to encode a cat, so it cannot do that. So if you see, in a data set of digits from 0 to 9, cat is an anomaly. So taking that into consideration, what we will do is that we'll take all the benign traffic that is coming from the internet, and we'll train an autoencoder out of it. Okay. So we train it with the benign traffic or any benign data. So what it will do, so when we pass a malicious traffic to it, so once it is trained, it will be able to reconstruct this. If it is x, it is x test, x set minus x will be nearly equal to 0, because it will be able to reconstruct it. But when you pass malicious data to this autoencoder, the same autoencoder will not be able to reconstruct that. It will be reconstructing something else. And if you take the difference between this, it will greater than 0. So to detect anomaly, we have to first train the network using the benign data. And once it is trained using benign data, in the future, when a benign data comes, it will be able to reconstruct it pretty easily. But when a malicious data comes, it will not be able to reconstruct it pretty easily. Then this value will be larger. Then we can set, so let's say this is the loss. We can set a threshold and say that if loss is greater than this threshold lambda, it is malicious. Else, it is benign or normal. You can also name this as anomaly. Okay. I hope this concept of anomaly detection is clear. And if you understand this, we can move forward with our discussion. So put in the chat if you understand this. We'll just do the next concept and the last concept of today, that is denoising autoencoder. So please let me know in the chat if you could or could not get this concept of anomaly detection using autoencoder. You can say I understood as well in the chat. Understood. Thank you. Okay. So we'll start the discussion of denoising autoencoder. So denoising autoencoder is that. So the name, it is evident that if there is an image of 7, but it is noisy, like there is some noise on top of it, or some part of this is missing, we should be able to reconstruct an original 7 out of it. Okay, you see what I'm saying? The idea is that given a noisy image, or given a not, like, not so good and safe image, we are able to do a fine image. So what we are doing is that, so the application of this will be like, there are some old photographs. Let's say you found some old photograph of a grandmom, mother or something. Some part is missing, some part is damaged. You still be able to create an original photograph of your grandmother. Okay. So how we'll do it? To do that, so we just have to train the autoencoder in that way. Let's say there is an image of 7, and so what, and it is noisy. So what you want is that we will pass this 7 to the autoencoder. Okay. And in the output, initially we will not get anything. Like it will also get like a random thing out of it, autoencoder. But so anything you get in the output, let's say you get that noisy 7, you have to compare it with the cleaned version of 7. Yeah. You have to compare it with a clean 7, because remember when we talked about the loss, how the machine model will it know which is noise and which is required. So we're not providing this as input, so we are providing 7 as input. So let's just think it in this way. The model initially will not be trained, so it will be just random model, initialized with random parameters. So what you're trying to say the model is that, so you're trying to give the model a goal. The goal is the loss. Okay, so you're trying to give the model a goal, and the goal is the loss. And so goal is the inverse of loss. Okay, and so when you're telling the model to do that, so you have to design the loss in that way. So if you could write your loss in a better way, you can the model will try to reduce the loss. So the model, when you start training the model, it always minimizes the loss. It always start to reduce the loss. So when we are talking about this, so it's not identifying if it is a clean image or not. It is just, internally it is trying to reduce the distance between this. So you are suppose, let's say this model is a human. Okay, and you are asking a human to make make the photo noise free. Okay, and you're just asking the human, and let's say you cannot talk, so you both belong to different country, you cannot talk. So what it will do, what you will do, you will just hand him the picture, noisy picture, and show him that, okay, just clean the noise. So of course he will not be able to understand that, so he will be doing something. Okay, so he will be doing something, not be like minimizing the loss. So when you do that, so then you can, what you do is that then you tell that if he does the denoising in one go, then you will tell that, okay, like now I mean, it is fine. But if you do not see the denoising that so if you do not see the denoising in the image, what you will do? You will again try to tell that, okay, this is the thing that you need to do. So with iteration, when you will talk to that person and he is coming up with doing something to the image, then you are saying, okay, you don't have to do this, you have to do that. And with iteration, he will try to refine the image and you will be able to get a clean 7. So he is not knowing that, okay, I mean, there is a noisy and there is a clean. So what you are sort of saying is that to make this noisy image like this 7. Okay. So the goal, so you're telling this model that this is my input image and this is my target image. So make the distance between this and this small. So what this autoencoder is doing is that it is designing the loss as this is x and this is x dash, x. What it is doing is that it is sort of trying to minimize this loss between x hat and x. Instead of this x as a clean image, now we are just providing a noisy image. That's it. By doing that, it will be able to know that, okay, I just need to minimize the distance between this image and this image. Yes, noise is part of the image as well. So we did that, and we sort of got this. So the goal is now different. We're sort of giving noisy image as input, and we're sort of getting and we want the image in the output as clean. And following the principle that I discussed earlier, this model will try to, in every iteration it will try to reduce that noise. And once we do that, and let's say the model is now well trained, now we can provide the model with a pretty noisy image. And since it has practice of cleaning this noise, it will directly clean the noise and give a clean image. You can now try with any model and it will give you the clear image. So while doing the coding of it, so we don't have noisy image. So in real world, we can get noisy image if we sort of find the image from the trash. But in real world, in the training, we don't have any noisy image. So what we will do now is that we will deliberately add some Gaussian noise to our image. Once we get the noise, once we find the Gaussian noise in the image, so we will use that noisy image as our input to the encoder, and we'll compare the output of the decoder with the clean image that we have. And with that, we'll teach the system that, okay, if the input is noisy, you have to output a clean image. And with that, in each iteration, we'll be able to figure out, so the model will be able to figure out, okay, this is the task I need to perform, and it will find the parameters which can do that. So I think time have 10, 15, 20 minutes left. So I'll just go to the code link, and then I'll just run the code for denoising autoencoder. I guess after that, you can attend your quiz as well. So let me go to the code page and try to run this. So if you, okay, so before moving to the code, did you get the idea of anomaly detection and the denoising autoencoder, or do you still feel blank? The denoising autoencoder is different in this way that now the input is noisy. Now the goal is that take noisy image and give me the clean image. Earlier the goal was take clean image and give me clean image. I don't care about these images. I just care about the intermediate output. Now it is saying that I don't care about the intermediate output, but I just care about the cleaned image. So now the goal is different. So the input to the model is different now. So did so so did you get this? Like, if you get this idea, like, you can put it in the chat, or if you have any doubt, you can ask me also. Okay, great. So we'll do the code now. So let's just, this is the code for animal detection. Put that as a title. Anomaly detection, and we run that. Then we have a piece of code to add the noise to to our image, because we want the noisy as the input as noisy and the output as not noisy. I did that. Then we define the autoencoder, and the autoencoder will be exactly same as the normal encoder, uh, decoder model, normal autoencoder, but only the output, the input to the model will be different. Now we will train the model. And train the model. Allow it for some time to get trained. I think you train 1 or 2 minutes, not more than that. The model is trained now. I got a question that training the model with good images. No, because if you see in the code, I'm getting the images and I'm adding noise to the image. It is clearly written, add noise to the image. So I'm adding noise to the image and I'm passing it and getting the output. So if you see, I'm passing this noisy image to the denoising autoencoder. Everything is clearly written in the code. If you just go through the code line by line, you can read it. So I add the noise to the images. I got noisy images and I'm passing the noisy images to the denoising autoencoder. I'm getting the outputs. I'm comparing the outputs and getting the loss using this loss variable from the outputs and the images. So the output is obtained by passing the noisy images and the images are clean. And then I'm updating as it is. So let me plot the training error for it. Okay, the training error is fine. Plot the original and the denoised image. So this will plot my, okay, dot detach. Dot to device. Let me see. I'm getting an error. I shouldn't be. Let me see. I'm plotting the image and train loader. Hmm. One 28 plus one plus. Okay. Okay, I see. The network here is okay. Uh, I'm getting an error, but I hope hmm, okay. I guess to this point it is fine. Okay, so I'm getting the title and train image, sample image, then denoising autoencoder, sample image. I'm getting a reconstructed image. Yeah, so this much I'm getting. So I'm able to get the deconstructed image, but I'm not able to plot it. So I guess the plotting code I need to take from here. It's coming at noisy, but it should be denoised. It hasn't. It didn't get trained properly, I guess. But you got the idea. Like the original image will be like this, like noisy. It will not be this much noisy, but it will be somewhat noisy, and uh, you'll be able to denoise it properly to get an exact score. So I'll be debugging this code, and I'll update the code in this notebook itself. I should have put this print this code earlier to see the error, but there is some error, I guess, in this training code that I'll that I'll fix it, and I'll update the code in this notebook itself. But uh, the idea is like that: we're training with by taking the noisy images, and we're sort of trying to find out a clear version of the image. So this is the noise, and this should be the original image. Okay, so I think we have discussed enough for today, and we have covered in this today's session, we have covered autoencoder and components of autoencoder, then types of autoencoder, and the activation function that we need to use in autoencoder. Apart from that, we also saw different application of autoencoder, starting with the compression, then slightly moving towards the reconstruction, and then denoising, and finally we saw some anomaly detection of using autoencoder. So, so I'll be continuing this discussion tomorrow, which will be the last day, and tomorrow we'll see how we can use RNN, which is another type of neural network, that is a recurrent neural network, to model sequences such as text data or time series data as such. So but till then, I'll try to, so my session ends here. I'll request ma'am to post the quiz link in the group, or if she has posted earlier, people can just go and attend the quiz, and best of luck for that. And I'll ask ma'am to close the session for today.
Thank you, Swain sir, for your valuable session and your key point-to-point explanation, and answering the questions to all the participants. And thank you very much, sir. And I thank all the participants for your active participation. Uh, Thank you so much, sir. We'll close the session. That means already we have given the quiz link, attendance link in your Zoom link call itself.
Okay.
Thank you all. Thank you.
Thank you. So I'll stop the screen share and recording. Thank you.
Okay, sir. Thank you.